Assalamu alaikum. I welcome you all to today's class. I'm sorry for the delay. I was stuck up in somewhere. So today we'll be again repeating yesterday's Plasmid Dna Isolation that many of the students complained were not able to comprehend because of poor connectivity. So hope today you have a good connection. Are you able to hear me?
Yes, sir. Yes, sir.
Okay, plus the quality of the YouTube video was also bad. So today I'll try to make a better video, then I'll upload the same. The board is visible. So we'll be doing plasmid DNA isolation today. So plasmid is a small extra nuclear DNA. If this is a cell, this is the genome DNA of a bacteria. So this is your plasmid DNA. It has its own origin of replication, so it replicates autonomously. Okay, and usually it has these antibiotic resistance genes that impart resistance against antibiotics. So we'll be isolating this plasmid today, okay, through the process we call as, hold on a second. Okay, sorry about that. So in plasmid DNA isolation, first of all, we have to grow the E. coli that is harboring this plasmid, and then we'll be extracting this plasmid. For that, we'll grow an overnight culture. And what we do, we use LB medium. LB medium is the medium that was made by Luria at Bertani. So that's why we call it LB medium. It's a complete growth medium for bacterial cells. So what we do, we have a Petri plate that's having colonies of bacteria. So in this case, we'll be using E. coli, from which we'll be extracting the plasmid, and this strain will be DH5 alpha. Okay, so this is a strain of E. coli from which we'll be isolating the plasmid. So what we do, we have this prior culture of E. coli. We take up a colony and then inoculate it in this broth and keep it for overnight at constant shaking at 37 degrees centigrade. 37 degrees centigrade is the optimal temperature of growth of bacterial cells. So we keep it at constant shakings on a shaker. This is an incubator cum shaker. So shaking ensures the mixing of ensures mixing of nutrients and aeration, proper aeration. So the other day we see that the broth is hazy because of the growth of E. coli cells. So what we do, the first step is we take this broth and we put it in a, say, microfuge tube. Microfuge tube, also called as an Eppendorf tube. It's a 2 ml, 1.5 ml. It comes in 2 ml. It comes in 5 ml. It also comes in 0.5 ml, 0.2 ml. So there's a range. So we can use 1.5 ml, 2 ml, or 5 ml, depending upon the quantity of the plasmid that you want to extract. So once we put the culture in this microfuge tube, then we centrifuge it for 5000 G for 5 minutes. So by doing so, what will happen? Your bacterial cells will make a pellet at the bottom, and you will have a clear supernatant in the top. So we discard the supernatant, and then you are left with the bacterial pellet. This is called as pellet, what sediments down due to centrifugation, and the upper portion is called as the supernatant, okay, that we discard. Now, there are three solutions that we use in alkaline lysis method. We call it as solution 1, solution 2, and solution 3. Solution 1 contains GTE, solution 2 contains SDS and NaOH, and solution 3 contains potassium acetate. Okay. Besides this, there are other solutions that we use, that we'll take after these solutions. So solution 1 contains GTE. G stands for glucose, T stands for tris, and E stands for EDTA. So why we keep GTE? Because this glucose in the GTE provides isotonic conditions so that our plasmid DNA does not come out beforehand, because we want it to come at a particular time out of the cell so that there are no DNases outside that will degrade the plasmid. So what we do, we add GTE, and if we have glucose, it will provide isotonicity so that the cells do not burst. Because you must have heard of, if you keep cells in a hypotonic solution, the salt concentration inside is high, so they will burst. And if you keep a cell in a high salt concentration, in a low salt concentration, okay, or in a high salt concentration where the concentration of salt inside is low, so it will shrink, because the water potential is higher inside, so water will move outside, so it will shrink. So that's how we provide glucose. Tris is a buffer condition. Here we want to maintain the pH of around 8. The pH of this is 8. This tris is around 25 millimolar working solution that we use. Glucose is around 500 millimolar. Okay, and your EDTA is around 10 millimolar. This is the working concentration of GTE in the solution, and the pH of this solution is 8 because of this tris. Tris is a buffer that undoes any change. It works on Lachatellier's principle or Lechatellier's principle, that if there's a change in the system, the buffer will undo the change and bring back the pH to 8. Okay, so it maintains the pH, and the role of pH is very important in this experiment, because as we move on, we'll come to know the importance of this pH, why we require the change in pH in this experiment to isolate our plasmid DNA. And EDTA, it is again a chelating agent like we saw in agrogel electrophoresis. It chelates the metal ions of the DNases if they are present. So once the metal ions like magnesium, that's an important entity of the DNases, once it gets chelated, the DNases are rendered inactive, so they cannot degrade our DNA. When the DNA comes out, they are not able to degrade our DNA. Okay, so what we do, we add solution 1 into this. If we are taking 1.5 ml tube in which we have put our this culture, so we will add 150 microliters of solution 1. So you have a tube, you have the pellet, you have the solution 1. So then you vortex it. Vortexing is a vigorous shaking so that the bacterial pellet is resuspended back into the solution 1. So once the pellet disappears and bacteria gets suspended in solution 1, then we add solution 2. Solution 2 contains SDS and NaOH. Okay, your NaOH is around 0.2 normal and your SDS is 1%. This is the fresh solution. The solution 2 we always make a fresh solution of solution 2. Okay, NaOH provides alkaline conditions, highly alkaline conditions, and SDS ruptures the cell wall and the cell membrane, and the DNA comes out. So SDS NaOH mixture brings about lysis of the cell because of presence of SDS. And NaOH, what it does, you have two strands of DNA. It denatures your DNA because at higher alkaline pH, the DNA denatures, and at lower pH it renatures. And also if you apply heat or temperature to the DNA, it denatures because hydrogen bonds breaks. And if you lower the temperature, they renature. The temperature at which DNA fragments denature is called as the TM, because TM is the temperature at which half of the DNA molecules they denature. Okay, that's called as the TM, or temperature of melting. So we don't want to go in that detail. So we have added here, here we have added around, say, 200 microliters of solution 2. That is 1 normal SDS and 2.2 normal, sorry, 1% SDS and 0.2 normal NaOH. Once we add the solution, what we do, if this is an up and off tube, earlier when we added solution 1, we vortex it vigorously on a vortex shaker. This is a small machine that I showed you yesterday. When you put the tubes in, it kind of puts the, when you put the electricity on, it kind of vortexes fast and the solutions mix. But when you add solution 2, you slowly swirl it like this, up and down. You are not supposed to vortex it at that point because that will shear your DNA, because now the DNA is out of the cell due to the addition of solution 2. It will break your DNA. You do not want that. Okay. So you'll swirl it like this until you see that the solution becomes mucilaginous. Okay. So once the solution becomes mucilaginous, that means the cell lysis has taken place. All the carbohydrates, all the proteins, all the lipids, fatty acids, your DNA, your RNA, everything is out of the cell. Okay, and becomes a mucilaginous type of a mass. After this, you add solution 3. This is the important step of plasmid DNA isolation. Why? You add 3 molar, 3 molar potassium acetate. Okay, you have this mixture, you have this mucilaginous mass. Okay, you add solution 3 to this. That will add around 300 microliters, and this is around 3 molar solution of sodium acetate. When you will put the sodium acetate in here, it will furnish K positive ions, and what has happened in the earlier step, your DNA has denatured because of NaOH, because of high pH. The pH of this is around 6 or 5 point, around 6. Plus it also has your 11.5% glacial acetic acid. Okay, this also helps in bringing down the glacial acetic acid, and this is a mixture of acetic acid, potassium acetate and glacial acetic acid. Solution 3, potassium acetate furnishes potassium ions, and glacial acetic acid brings down the pH. At lower pH, the hydrogen bonds tend to again renature, and plus the DNA strands are separate because you had these negative charge, and the negative charge on the DNA is because of phosphates. Okay, so phosphate gives the net negative charge to the DNA. So when these potassium acetate furnishes potassium ions, these potassium ions neutralize this charge, and once this repulsive force between these two strands is neutralized, the strands come together and again renature. But once you add this solution, you have to keep it on ice for 2 minutes. Okay, so brings down the ice brings down the kinetic energy, because if you have two strands and they are in kinetic motion, so it's harder to form bonds. Okay, so when you put it on ice, so the kinetic energy of these DNA molecules decrease and they form the hydrogen bonds. So now the trick here is we only have to put this for 2 minutes on ice, because we know our mixture contains your genomic DNA that we do not want and your plasmid DNA that we want. Genomic DNA is large, so to renature genomic DNA, it takes more time, and plasmid DNA is small, so it takes less time. So we want that we only keep this mixture or solution, after adding solution 3, we keep it only for 2 minutes on ice, because if we prolong the incubation on ice, genomic DNA will also renature, and renatured DNA is lighter, less dense than the denatured DNA. When DNA is denatured, it's dense, its density increases. When it renatures, its density decreases. So this is the most crucial step in the whole extraction process, because here we do not want, we want to negate this or take out this genomic DNA, and we only want this plasmid DNA. We should not have a contamination of this genomic DNA. That's the important step. So that's why after adding, we mix it a little bit, put it on ice for 2 minutes, and then centrifuge it for 15,000 G for 15 minutes. So now what has happened here, we have given it 2 minutes, plasmid was small, it renatured, it becomes less dense. So when we centrifuge it, it will be in the supernatant. Genomic DNA was just thinking, okay, I have to now, okay, now they have added solution 3 and they have put me on ice, now I will start to renature. He was only thinking that I will renature, but we did not give it time, we centrifuged it. So centrifugation, what happens, genomic DNA being a single stranded or denatured form, it will be heavier, and it will be, after centrifugation, it will settle down with your proteins, your lipids, and you have your genomic DNA and your fatty acids, your carbohydrates, all will settle down except for your plasmid that will be in the supernatant. Okay, clear? So what we do then, we pipette out this upper layer carefully. We should not take this zone. So slowly we'll pipette it out and put it in a fresh tube. Once we put it in a fresh tube, so this is a fresh tube, you have an aqueous solution, this is an aqueous solution, and this aqueous solution has your plasmid DNA, but it's in the soluble form. Now what we do, we add isopropyl alcohol or ethanol. Absolute. Absolute means 100%. We add, if we are writing isopropanol, this is your tube. If this is, say, 500 microliters supernatant, we will add 500 microliters of isopropanol. What we call as equal volumes. We will add equal volume of isopropanol. That means अगर ये 500 है, it's 500. Your plasmid solution, aqueous solution, will add 500 microliters of isopropanol. However, if you are using ethanol, you will use double the volume. That means if this is 500 microliters, you will add 500 plus 500, that is 1 ml. You will add ethanol. So what it does, the DNA is in the solution form, but once you add this isopropanol in this, it will decrease the dielectric constant of the solution. Once the dielectric constant decreases, so DNA is precipitated out. So the function of isopropanol brings down the dielectric constant. Water has the highest dielectric constant at which, so solubility of anything in a solvent is determined by the dielectric constant of that solution. So since water has a high dielectric constant, its DNA is dissolved in it. So but when we bring down the dielectric constant, it precipitates out. So adding isopropanol precipitates out DNA, then we centrifuge it for 5000 G, 15,000 G for 15 minutes. And you will have a pellet of DNA or plasmid DNA below, and then you have this solution, ethanol and water solution. You will throw this out or decant this out, and then you will add 70% ethanol. 70% ethanol we add because there's salt contamination in this plasmid DNA, and after this experiment, when we have isolated the plasmid DNA, we'll restriction digest it, or we'll clone it with something, okay, or we'll transform it. So these salt impurities, they can hamper our reactions, our future reactions. So we need to remove these salts. So what we do, we add 70% ethanol. 70% ethanol. If you have 100%, 70% ethanol, that means you have 70 ml water plus 30 ml of, 70 ml of ethanol and 30 ml of water. That makes 70% of ethanol. So you add it, you wash it. So in the 70% of ethanol, the dielectric constant is such that the salts will come out and will be dissolved in your solution. But DNA will not be solubilized. It will be in the precipitated form. So once adding it, we'll swirl it, and then we'll again centrifuge it for 5000 G for 5 minutes. And you have the DNA pellet here, salts are here. We'll throw this out, the supernatant, then we air dry it. Air dry it for 20 minutes in a laminar flow, or it can take 1 hour. So once you air dry it, if there's any residual ethanol, it should be removed, because if there is some ethanol, you'll try to solubilize the DNA, it will not be solubilized. So we have to ensure that ethanol is all evaporated, so that's why we air dry it. So once the ethanol is evaporated, we add TE solution, say 100 microliter, to dissolve the DNA, and from prolonged storage. Because you have tris here, tris maintains the buffer conditions, and E is your EDTA. And if there are some DNases by chance going to the tube, our DNA will not get degraded because of these DNases, because we have EDTA, and EDTA will chelate the metal ions that are necessary for the action of DNases, and our DNA will be protected. And then once the DNA dissolves, you will run it on a gel. You will run it on a gel Now, for example, PGFP vector is 4.7 kb. This was the PGFP or any vector we have isolated. The size of this is 4.7, and you have a ladder here. So this is 1, 2, 3, 4, and 5. So when you run it, the band should be between 4 and 5, 4.7 kb, right? What we studied in first two practicals of agrogel electrophoresis, that the ladder bands corresponds with the molecular weight of the DNA that we have loaded. But in this case, when we run a plasmid DNA, we do not see one band, but we see 3 bands or 4 bands, what we call as multiple bands. Why? Because the plasmid that we have isolated has 3 conformational forms. This is the open circular, this is supercoiled, and this is highly supercoiled. So supercoiling is a process through which DNA tries to relax itself, okay, because this supercoiling is nothing but they are wreaths, and I'll show you. For example, say this is your DNA double strand, this is one strand and this is other strand, so 2 strands of DNA, so this is the double helix. So when the DNA overwinds or underwinds, the number of base pairs per turn increase or decrease. So this brings about the pressure in the DNA, and due to which once we do like this, they will form secondary structures. These are called as wreaths. These are called as twists. These are called as wreaths. So when the wreaths form, the DNA relaxes. So these are nothing but these are the wreaths. So this process is called as DNA supercoiling. The number of twists plus number of wreaths is called a linking number. We do not want to go into the detail. Linking number of a DNA molecule is constant, and linking number is your topological bond that keeps 2 entities together. For example, if this is 2 DNA circular DNAs, they are together with the help of an imaginary bond that keeps them together. They cannot come out of each other. So this bond is called as a topological bond that's present in the DNA because it's circular, it is double-stranded. So what happens due to the supercoiling? This bigger molecule is not able to move as fast as this smaller molecule. Means I'm talking about the shape. The size is the same 4.7. So the bigger molecule will be will be difficult for him to move through the matrix of the gel. So it stays back. There's a little bit drag and it stays back. So the bigger band is the higher band is of this one. So this one is a little bit quicker than this because it's now a little bit thinner. So it can move in the matrix. So it will be faster than this open one. So you'll have a band here. And this one is the slimmest of all. So it can easily move faster than these two, and it will form a bond below these two. So that's why when you run a DNA, plasmid DNA on a gel, you see 3 bands. If you run genomic DNA, you will see 1 band near the well because the genomic DNA is heavier. That's why you see 1 band near the well. If you have a smaller DNA, say PCR fragment, that's 500 kb, you will see it here. If it's 3000 kb, you'll see it here. So the molecular weight of this is determined by the ladder, molecular weight ladder, that we usually run with our DNA in agrogel. Is that clear?